The U.S. has new intelligence
of a, quote, serious national security threat.
Nukes in space, really?
In the heart of the Cold War, the United States explored an unprecedented and controversial frontier: nuclear weapons in space. It is now, decades later, that we're beginning to see the shocking extent of these plans to use nuclear bombs as weapons of war. In space. This set the stage for a new chapter in both space exploration and global security. But while these nuclear ambitions were grounded in scientific promise, they also led to profound questions about the dangers of tampering with forces far beyond our planet. Hang tight as we unveil declassified details about how the United States nuked space and changed the world. Let's get started. When the United States nuked the space. On July 9, 1962, spectators gathered all over Honolulu to witness an event that would forever alter the course of both space exploration and global security. What they were about to see was no ordinary display. Following a brilliant flash of light that turned the night into day, they witnessed an immense glowing fireball that rapidly expanded in the upper atmosphere. This was soon accompanied by vivid auroras in shades of green, blue, red, and pink. These auroras illuminated the night sky for several minutes, casting an otherworldly glow that extended as far as Hawaii, New Zealand, and parts of the United States. This was history in the making. The United States had just tested a thermonuclear weapon in outer space. Today, we'll explore the true extent of this plan and the risks involved. Let's carry our story further. This dramatic event, known as Starfish Prime, was part of the United States' ambitious and controversial attempts to test the boundaries of nuclear power. The Starfish Prime test, a high-altitude thermonuclear explosion, was detonated 400 kilometers above the Pacific Ocean, far beyond the Earth's atmosphere. The explosion, with a yield of 1.4 megatons of TNT, was designed to test the effects of nuclear detonations on the Earth's magnetosphere. Following the visuals created by the explosion, as noted earlier, an intense burst of radiation disrupted satellite communications, caused damage to electronics, and even sparked a global debate over the future of nuclear warfare. This event marked the peak of a series of nuclear detonations conducted in Earth's atmosphere, and it was the first and only time the United States detonated a nuclear device in space. The test unfolded in the backdrop of the brutal arms race during the Cold War, which pinned the United States and the Soviet Union against one another, each vying for technological superiority, not just on Earth, but in the vast, uncharted reaches of space. One can only imagine, based on the details of this event alone, how close the world had come to a catastrophic event. In the early years of the space race, both nations explored the idea of nuclear weapons in space, not only for military purposes, but also for testing their potential to alter the dynamics of space travel. These early experiments, while heavily classified at the time, later revealed just how fragile the line between science and geopolitical conflict was. To better understand the fragility of the situation, we'll take a walk through history. The era of space-based nuclear tests. In the 1950s and 1960s, the Cold War set the stage for one of the most ambitious and dangerous experiments in human history: nuclear detonations in space. Through operations Hardtack, Argus, and Fishbowl, the United States revolutionized our understanding of space, radiation, and the delicate relationship between human-made technology and Earth's natural defenses. However, the stunning effects of these tests also led to growing concerns about their long-term consequences, culminating in the 1963 treaty that aimed to curb atmospheric and high-altitude nuclear explosions. It all started with the Operation Hardtack in 1958. These were a series of nuclear tests primarily conducted in the Pacific Ocean. The operation's purpose was to test the effects of nuclear detonations at high altitudes, providing essential data for both military and scientific applications. Though most of the tests took place in the atmosphere, several were carried out at stratospheric altitudes, reaching heights where the atmosphere thins and the potential for creating cosmic effects increased. Operation Hardtack yielded temporary auroras or colorful light displays due to the interaction of nuclear explosions with the Earth's magnetic field and ionosphere. These artificial auroras were a sign of the powerful electromagnetic forces unleashed by the detonations. Additionally, the high-altitude tests disrupted global communication systems by inducing electromagnetic interference, providing a first glimpse of how nuclear explosions could affect not just the environment, but also the delicate technological systems humans were beginning to rely on in the modern world. Later in 1958, the United States launched Operation Argus. These were a series of nuclear explosions conducted at low altitudes in space, specifically aimed at creating artificial radiation belts. This operation, which involved detonating 3 low-yield nuclear bombs at altitudes ranging from 100 to 300 kilometers, aimed to study the interaction between nuclear explosions and the Earth's magnetic field. The results were extraordinary. The explosions produced artificial radiation belts that mirrored the radiation belts created by the Sun, but with a far more intense and dangerous form of radiation. The creation of these belts revealed how human activity could influence the structure of Earth's magnetosphere, potentially endangering satellites and spacecraft. The tests also revealed the potential for human-made radiation to interfere with the operation of electronics, causing lasting concerns about the safety of space missions and the vulnerability of Earth's space-based infrastructure. Though Operation Argus was not widely publicized, it laid the groundwork for future tests that would explore the limits of nuclear effects on both Earth and outer space. As the 1960s progressed, the US escalated its nuclear testing program with Operation Fishbowl, a series of high-altitude nuclear tests aimed at exploring the effects of nuclear explosions on Earth's magnetosphere, among other objectives. The operation, conducted as part of the larger Plumbob series, included several tests, but not all were successful. One notable failure was Bluegill Prime, a test that did not achieve the desired results. However, the most significant and groundbreaking event of the operation was Starfish Prime, which became one of the most studied and impactful space-based nuclear explosions in history. But why? Why make the space an arena for geopolitical conflict? Let's dig in. Ambitious nuclear plans for outer space. Amidst the geopolitical rivalry fueled by the Cold War, both nations harbored ambitious and, at times, dangerously speculative ideas about using nuclear technology to achieve unprecedented space exploration goals. While many of these plans were never realized, they offer a chilling glimpse into how nuclear technology was once viewed as a means of propelling humanity beyond Earth and into the depths of the solar system. For instance, the idea of nuclear propulsion was tantalizing. Theoretical scientists proposed that nuclear-powered rockets could revolutionize space travel by drastically reducing the time it took to reach distant planets. These systems would use nuclear reactions to generate propulsion, either by using nuclear thermal rockets that heated propellant via nuclear reactors, or by direct nuclear explosions to create thrust, what some referred to as nuclear pulse propulsion. The benefits were clear. Using nuclear propulsion would allow spacecraft to achieve speeds that conventional chemical rockets could never match. Under such systems, humanity could potentially reach Mars in months rather than years. However, the challenges were immense. The most significant hurdle was ensuring that the technology would be both practical and safe. While nuclear propulsion systems would provide superior efficiency and speed, the engineering challenges of controlling and harnessing such power in space were formidable. Additionally, the radiation risks, both from launching nuclear-powered rockets and from possible radiation exposure in deep space, posed a threat to both astronauts and the environment. These concerns led to the abandonment of most nuclear propulsion projects, although some modern-day concepts, like NASA's Project Orion and the concept of nuclear fusion propulsion, are still being explored. However, amidst the race to conquer space, the United States came up with Project A1119, one of the most bizarre and controversial nuclear space projects ever. Conceived in the late 1950s during the early years of the space race, Project A119 was a secret US Air Force plan to detonate a nuclear bomb on the moon. Yes, you heard that right. The Soviets had already launched Sputnik, the first artificial satellite, and sent the first living creature, Laika the dog, into space. Fearing that the Soviets might undertake their own plans to explode a nuclear device on the moon as a demonstration of power, the United States sought to get ahead of them by conducting its own nuclear experiment in space. Project A119 was envisioned as a way to both scientifically study the moon's surface and send a bold message to the Soviet Union about America's technological capabilities. The planned nuclear explosion would have been a massive thermonuclear device capable of creating a brilliant flash visible from Earth. Scientists predicted that the explosion would release an enormous amount of energy, vaporizing a portion of the moon's surface and sending a cloud of debris into space. The resulting crater could have been several kilometers wide. This demonstration of power, however, was not without its own technical and ethical concerns. The long-term consequences of detonating a nuclear bomb on the moon would have been severe. The moon's surface would likely have been scarred for centuries, if not millennia, and the radioactive fallout would have lingered, potentially altering the lunar environment permanently. Additionally, the explosion could have had lasting effects on future lunar missions, with concerns about radioactive contamination of lunar soil. There was also a serious concern that the Soviets, not to be outdone by the United States, might themselves conduct a similar experiment. Thankfully, the Project A119 was eventually scrapped. The US government, under the guidance of President Dwight D. Eisenhower, opted for a more measured approach to space exploration. Rather than taking the risk of nuclear detonations on the moon, America pursued peaceful lunar exploration, culminating in the Apollo missions. Though such ideas may seem like something out of science fiction today, they were once taken seriously by some of the world's most powerful nations. But wait, we're just getting started. The Orion Project. Conceived in the late 1950s, the Orion Project was an attempt to leap beyond the limitations of conventional rocket propulsion. The project's goal was to develop a spacecraft powered by nuclear explosions, specifically nuclear bombs, that would be detonated behind the spacecraft, creating thrust. Known as Orion nuclear spacecraft, these rockets would use the force of multiple detonations to propel a craft through space at unprecedented speeds. This nuclear pulse propulsion had the potential to make interplanetary travel not just a possibility, but a practical reality. Theoretically, the Orion spacecraft could reach Mars in a matter of months, far quicker than any chemical propulsion system could achieve. However, the Orion project was not without its dangers. The most significant concern was the prospect of detonating nuclear warheads in space. In theory, the use of nuclear explosions behind a spacecraft would provide powerful thrust, but the risks were massive. One of the most critical issues was the potential for detonations to go wrong during launch, which could turn the areas surrounding the spacecraft into radioactive wastelands. The idea of nuclear bombs being exploded in Earth's atmosphere and then scattered into space was an unnerving prospect. Perhaps the most alarming danger involved the crew who would be on board the Orion spacecraft. The spacecraft's propulsion system would subject the crew to extremely high doses of radiation, estimated at over 700 rads, well beyond the safe limits. This is essentially a lethal dose of radiation, potentially causing immediate health effects like radiation sickness, severe organ damage, and death. While the Orion spacecraft was designed with shielding to protect astronauts from the worst of the radiation, it was clear that such exposure was untenable for long-duration space missions. Scientists working on the Orion project proposed solutions to reduce the risks associated with nuclear propulsion. One of the most discussed options was the development of cleaner nuclear bombs, those that would produce less radioactive fallout or have more controlled bursts of energy. These bombs would theoretically minimize the environmental and human health risks posed by their detonation, though questions about their practical application in space remained. The project faced growing scrutiny in the early 1960s, particularly in light of increasing public concerns about the dangers of nuclear testing. In 1962, President John F. Kennedy decided to take a firm stance on nuclear testing. which would ultimately lead to the partial nuclear test ban treaty signed later that year. The treaty sought to prohibit nuclear explosions in space, underwater, and in the atmosphere, a response driven by concerns over the environmental and geopolitical consequences of unrestricted nuclear detonations. Kennedy's response effectively sealed the fate of the Orion project. By the mid-1960s, Project Orion was effectively terminated. However, the ideas behind the project left a lasting legacy. The pursuit of nuclear propulsion, though ultimately infeasible in the mid-20th century, continued to spark scientific curiosity and inspire future generations. Today, more advanced and less dangerous forms of propulsion, such as ion drives and the development of nuclear fusion technology, are being explored as viable means to propel spacecraft further into the solar system. But going back to the Cold War, the nuclear threat was not over just yet. Star Wars Strategic Defense Initiative. In 1983, US President Ronald Reagan unveiled his ambitious and controversial plan to protect the United States from Soviet missile attacks. The Strategic Defense Initiative, or SDI, famously known as Star Wars, employed space-based technology to create an impenetrable shield against nuclear threats. Unlike the traditional deterrence strategy of mutually assured destruction, SDI proposed the use of space-based lasers and other advanced technologies to intercept and destroy incoming Soviet missiles long before they reached American soil. This visionary concept promised to change the nature of global security, allowing the United States to Star Wars the Soviet threat from the sky. On the surface, SDI was seen by many as a technological leap that would make nuclear war unthinkable. But, as with many bold ideas, it faced substantial technical, political, and financial hurdles. For example, one of the more outlandish components of the Star Wars initiative was the development of the Casaba howitzer, a space-based weapon that relied on thermonuclear explosions to generate a focused plasma beam. This weapon sought to use the energy of a nuclear detonation to create a directed, concentrated beam of energy capable of neutralizing missiles from thousands of kilometers away. The Casaba howitzer concept was based on the idea that a small nuclear explosion could generate enough heat and plasma to form a beam that could destroy a target at a great distance. However, critics questioned the feasibility of such a defense system. After all, the complexities of controlling a nuclear explosion in space and the risks of using such destructive technology in orbit cannot be complicated. Naturally, the Casaba howitzer never materialized. Similarly, the Excalibur project sought to use lasers as a primary method for missile interception. The idea was to harness thermonuclear energy to power X-ray lasers to shoot down Soviet warheads. Early tests of the Excalibur system showed some promise, with prototypes capable of firing lasers over short distances and delivering destructive power. However, as development continued, significant flaws became apparent. The lasers lacked the necessary strength to be effective, and their reliability was a major concern. Moreover, powering these lasers in space, while maintaining a consistent and focused beam, proved much more complex than initially anticipated. Despite early optimism, the Excalibur project ultimately failed to deliver a viable defense solution, and the promise of space-based lasers remained elusive. While the technological shortcomings of SDI were evident, the mere existence of the Star Wars initiative had a profound effect on international relations during the Cold War. The Soviets feared that SDI could undermine their nuclear deterrent, giving the US a strategic advantage and potentially tipping the balance of power in favor of the West. Naturally, they began to engage in more earnest arms control negotiations, leading to a series of treaties that would help limit nuclear arms production and testing. Moreover, the SDI was never fully deployed, and the Star Wars vision of space-based missile defense remained a dream. The high costs, technological limitations, and lack of political will contributed to the project's eventual termination. In 1993, President Bill Clinton effectively put an end to the SDI program, redirecting funding toward more conventional missile defense systems. But the idea of using nukes in space was not scrapped altogether. nuclear weapons, and asteroid defense. It was a massive asteroid impact that killed off the dinosaurs. So, what if it happens again? Well, there is a probability that it will. However, the likelihood of a direct impact remains low. In any case, if such a thing happens, the consequences could be catastrophic, triggering mass extinctions or devastating global disasters. So, what are our options? Well, the United States has considered the use of nuclear weapons to defend Earth from an asteroid strike. NASA has tracked over 1 million asteroids, with 2,300 of these considered hazardous to Earth. These asteroids, ranging in size from a few meters to several kilometers, orbit the Sun and occasionally cross Earth's path. While most pose no threat, larger asteroids, those between 1 and 10 kilometers in size, could deliver a serious hit. An asteroid of this size, capable of generating the force of millions of megatons of TNT, could obliterate entire cities or even cause a mass extinction event, similar to the one believed to have wiped out the dinosaurs. The threat is real enough that NASA has devoted significant resources to tracking near-Earth objects, or NEOs, and understanding the potential impact risks. With advancements in space observation and detection technologies, scientists are identifying more of these hazardous objects and assessing the likelihood of an impact. If push comes to a shove, we can detonate a nuclear missile near an incoming asteroid to either destroy it or, more commonly, deflect its path away from Earth. Nuclear explosions can release enormous amounts of energy in a very short time, and theoretically, this energy could alter the trajectory of an asteroid, preventing a catastrophic collision with Earth. To stop a large asteroid, a planet-killer asteroid with a size of 1 to 10 kilometers, an explosion would need to release around 100 gigatons of energy. In comparison, the combined nuclear stockpile of Earth's nuclear powers is a fraction of this amount, making it clear that the scale of the challenge is astronomical. Additionally, the method of detonating nuclear weapons in space poses significant challenges. For one, the effectiveness of such a strategy depends on the asteroid's composition. A nuclear blast might shatter a rocky or icy asteroid, but it would be far less effective against a dense, metal-rich asteroid. Furthermore, the blast's proximity to the asteroid would need to be precise. A miss could have disastrous consequences, altering the asteroid's path in unpredictable ways. Then there are international treaties that prohibit such actions. The Outer Space Treaty, signed in 1967, explicitly forbids the use of nuclear weapons in space, stating that space shall be used for peaceful purposes and that countries should avoid harmful interference with other nations' activities in space. However, the idea has not died out. In 2023, researchers at the Lawrence Livermore National Laboratory achieved a significant breakthrough in asteroid defense research. They discovered that X-ray radiation from thermonuclear explosions could potentially be used to deflect large asteroids, especially those made of silicate rock or quartz. The idea is that the intense X-ray radiation could vaporize the surface of the asteroid, creating a recoil effect that would push the asteroid off course. While this finding offers new hope, it also comes with its own set of limitations. Besides the accuracy requirements and yield limitations, the most daunting aspect of any asteroid defense plan, whether nuclear or otherwise, is the timing. The precision required to intercept an asteroid years before its predicted impact is incredibly difficult to achieve. Even with advanced technologies like space-based telescopes and automated tracking systems, there is a considerable margin for error in predicting an asteroid's path. This creates a challenging situation, as scientists would need to act well in advance, sometimes decades before an asteroid's projected collision with Earth, to ensure that the deflection works. Furthermore, there is the added risk of overcorrecting the asteroid's path, sending it toward a different part of Earth with disastrous consequences. Even if the asteroid is successfully deflected, the potential for miscalculations and unforeseen effects makes this a high-risk strategy. But what if we didn't just have one Earth? Well, nukes come into play in that scenario as well. Space colonization and terraforming. Mars with nuclear weapons. In the quest for space exploration and colonization, few ideas have captured the imagination more than the prospect of transforming inhospitable planets into thriving ecosystems. Mars, often referred to as Earth's sister planet, has long been a prime candidate for terraforming. There are a bunch of different ways this can happen. One of them is via the use of nuclear weapons. The idea has been championed by entrepreneurs like Elon Musk. He intends to detonate nukes over Mars's polar caps. The explosions would release massive amounts of greenhouse gases, such as carbon dioxide, into the atmosphere, effectively warming the planet and thickening its atmosphere to support human life. The process would mimic the natural phenomenon of a runaway greenhouse effect, similar to what Venus experiences, but in a controlled manner. By heating the polar ice caps, carbon dioxide would be released, triggering a chain reaction that would gradually warm the Martian surface, raise atmospheric pressure, and potentially enable liquid water to flow on the planet. While the idea is fascinating, it raises several critical questions about the practicality and effectiveness of this approach. The proposed benefits of such an approach, warmer temperatures, a thicker atmosphere, and more stable conditions for human habitation, are alluring. However, the reality is far more complex. The most significant barrier to Musk's nuclear terraforming proposal lies in the sheer scale of destruction required. According to scientific calculations, to create a substantial warming effect on Mars, a staggering 3,500 thermonuclear bombs would need to be detonated daily over a period of 7 weeks. This would equate to over 245,000 bombs in total. Even though thermonuclear bombs release enormous amounts of energy, the amount of explosive force needed to generate enough greenhouse gases to alter Mars' climate is far beyond humanity's current capacity. Moreover, this strategy faces several additional issues. For example, despite the vast energy released by the explosions, Mars' thin atmosphere and low gravity may not allow for atmosphere, composed mainly of carbon dioxide, is much thinner than Earth's, and even if greenhouse gases were released, they might not remain long enough to have a substantial warming effect. Mars also lacks a protective magnetic field to shield the atmosphere from solar winds, further complicating the long-term viability of this strategy. Additionally, the detonation of so many thermonuclear devices would pose immense radiation hazards, both on Mars and in its vicinity. The potential for radioactive fallout could further degrade the planet's already harsh environment, making it even less conducive to supporting life. Finally, the number of bombs required exceeds the global stockpile of nuclear weapons by far. At present, there is no country on Earth with nearly enough thermonuclear warheads to implement such a strategy, making it, for now, a purely theoretical exercise. Naturally, some scientists have proposed alternative approaches to make Mars habitable. One such idea is to remelt the Martian core to reactivate the planet's magnetic field. Without a strong magnetic field, Mars's atmosphere is vulnerable to solar wind, which strips away much of its atmosphere over time. Reactivating the core could provide a protective shield from solar radiation and allow for a thicker, more stable atmosphere to develop over time. However, the sheer amount of energy required to remelt Mars's core would require an astronomical number of thermonuclear bombs. Estimates suggest up to 8 trillion. Opening up new frontiers in space exploration. The idea that nuclear weapons might one day be used for space exploration, planetary defense, or scientific research challenges the historical perception of nuclear technology as purely destructive. We've already explored the first two options and their likelihood. But nuclear devices could also be utilized for scientific purposes, such as conducting experiments in space that require the extreme conditions provided by thermonuclear explosions. These experiments could provide insights into the origins of the universe, matter, and energy, while also advancing our understanding of fundamental physics in environments far beyond Earth. Despite the potential benefits of using nuclear technology in space, the ethical implications are significant. The concept of deploying nuclear weapons, even for peaceful purposes, is fraught with moral and environmental concerns. The detonation of nuclear devices in space raises the risk of long-lasting environmental damage, including the creation of radiation belts that could pose a threat to both human explorers and satellite systems. Furthermore, the possibility of future conflicts in space, driven by the availability of powerful nuclear technologies, presents a serious concern. As space exploration becomes more accessible to both nations and private enterprises, the temptation to use space-based nuclear technology for military advantage could increase. International treaties, such as the Outer Space Treaty, aim to prevent the militarization of space, but the rapid pace of technological advancement in the space sector may outstrip regulatory frameworks, creating new risks for global stability. In the past, the idea of exploding nuclear weapons in space was largely unchallenged due to a lack of awareness about the long-term environmental and technological consequences. The United States, having already demonstrated the destructive power of nuclear weapons with the bombings of Hiroshima and Nagasaki in 1945, continued to test nuclear devices in the Pacific, including high-altitude detonations. These tests, such as the Starfish Prime test in 1962, were seen as scientific endeavors or necessary military preparations, with little consideration given to their broader impacts on Earth's environment, infrastructure, and technological systems. At the time, there was minimal understanding of how such explosions could affect space weather, satellites, and global communication systems. However, the global landscape has dramatically shifted, with far greater awareness and technological sophistication today. The potential consequences of detonating nuclear weapons in space are now understood to be catastrophic, not only in terms of radiation and environmental harm, but also due to the vulnerability of satellite infrastructure, communication systems, and power grids. Moreover, such a display would likely trigger an immediate arms race, with countries like Russia and China potentially matching or exceeding the United States in the development of space-based nuclear technologies. The creation of artificial radiation belts, electromagnetic pulses, and the risk of permanently damaging the Earth's magnetosphere makes such actions far riskier than they've ever been in the past. Moreover, the future of space exploration is increasingly focused on innovative, non-destructive technologies that can expand our reach in the cosmos. One notable example is the James Webb Space Telescope, which offers unprecedented views of the universe, providing insights into distant galaxies, the formation of stars, and the potential for life on exoplanets. Another promising frontier is the development of solar sails, which harness the pressure from sunlight to propel spacecraft, enabling long-duration missions to distant stars without the need for conventional fuel. These advancements, along with other technologies such as ion drives and autonomous exploration rovers, represent a more sustainable and peaceful approach to space exploration. They offer a path forward that emphasizes scientific discovery, international collaboration, and the potential to unlock the mysteries of the universe, all without risking the damages caused by nuclear tests in space. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.